All right. Good morning. Good morning, everyone. Let me remove this so you can see my screen. So let's get started with today's class. For today, my goal is to finish the lecture that we started last class, where we're talking about completely randomized design and more specifically. And then after we finish that, my goal then is going to be for us to actually do a hands-on exercise where I want to show you a workflow that I use every time that I'm doing this type of analysis. However, it was not something that I really learned in a class. It was more something that I guess you end up developing by doing it and realizing what's needed, what you should keep in the analysis, and what parts make its main components. So we're going to go through that after we finish the lecture as well. All right, so for the lecture part, basically just going to continue what we were started last class, which is on my website. So it was this lecture here from January 30th. If you want to follow along from there, you're welcome to. We're going to quickly recap what we saw already and then continue the conversation here. In the last class, we really had a lot of great comments, great questions. I do encourage you to ask me things as we are going through, because really, the goal of this is to be very applied, especially so you hopefully can connect these concepts with your research and also be thinking of how they impact what you do. And so I do welcome these questions and conversations. I think everyone gains from them. Okay, so getting back to this lecture here, so we're more specifically talking about completely randomized design, but because it is the first design that we're going to explore a little bit more detail, I need to introduce you to some topics that apply to any design analysis. So things like, so we talked about the homogeneous experimental unit, how that impacts our treatment randomization, the effects model. I think we stopped last time at the ANOVA table. We're going to revisit that one more time and going to talk a little bit about it because, again, the ANOVA table is going to be really important for you to understand how things are happening behind the scenes, and not necessarily from like a purely mathematical way, which is something that you probably already learned on your stats courses, but more just from understanding what is really happening in each one of the stages that we're doing in the ANOVA, and that knowledge is going to be able to help you first to check if your model that you're specifying really reflects your design, which again is something that's going to come from you, the researcher. R, SAS, Python, whatever it is going to give you results regardless. You can give a completely wrong design or a completely wrong model compared to the design you used, you're still going to get results from the software. So it's not going to yell at you saying you're doing something wrong. So that's going to depend on you to know that you're really providing the correct model. And then we're going to talk about the linear model assumptions. If you've taken any other stats courses that talked about design, I would assume that you're already familiar with them, but we're really going to dive more into that. And I think that's what I have planned for this lecture. So we did have this example here that we're talking about a two-way factorial where we had 3 nitrogen fertilizer rates and 3 potassium rates for a total of 9 treatment combinations. I'm going to just skim very quickly through the parts that we've been through, but if you do have any questions, let me know. In this case here, we are assuming that we have homogeneous experimental material. So this could be same soil type, same topography, perhaps, you're using in the greenhouse, the greenhouse is built in a way that you don't have gradients of temperature or radiation, solar radiation, or moisture or anything like that. And when we do have that, then completely randomized design is the option that we would choose. One of the very specific things about this design here is that we randomize treatments without any restrictions. So as we already talked about, And randomization is key in any, so again, perhaps one of the main differences between experimental design analysis and other things, which include machine learning, is that in design studies, we have the chance and the choice of doing randomization, especially within experimental units that are homogeneous. That is one of the main points of experimentation, because that allows us to make a whole bunch of assumptions and also to make our model, being able to use that model to have more of a cause and effect relationship, which is something that normally we cannot make that assumption with observational data that we're not controlling. So in this case, randomization really gives us that power. So in our example, we were doing unrestricted randomization, where we had 4 reps. So we decided to have 4 replicates in this study, and that would bring us to a total of 36 experimental units. And then now is the question of, can I fit whatever fit means? So it could be a given size plot you're using, it could be maybe number of pots on the bench, maybe number of plants in the plot, whatever that is for your case. Can we fit 36 experimental units in homogeneous material, right? So here we're assuming yes, we can. So then we had this example here with 9 treatment combinations, and just highlighting treatment 1 and how that is, just we had treatment 1 happening twice in the first column and not happening at all in the third column. And that's okay because we're assuming our material is homogeneous. Then we talked about the effects model, which, it is a formula that it really is telling us what are the effects that we're considering in this analysis, which the model itself, you may look at it and think, well, how does that have an impact on my analysis? Well, whenever we code this this model is going to directly connect with that, which also is going to directly connect with the ANOVA table. So each one of these effects in this model are actually going to be aligned in your ANOVA table. And that's another way that you know that at least you're specifying what you should. And this is the model for the completely randomized design. In this case here that we're having our motivational example, we have a 2-way factorial, right? So really the design component of it is not explicit in the formula. It is basically just ending up in the error, which is the EIJK term. And then we have an overall mean that every model is going to have. We have the effect, in this case here, alpha I is the effect of nitrogen rate, where I equals to each one of those nitrogen rates. So we have 3 alpha coefficients being calculated in this model, 1 for each one of the rates. The beta coefficients are calculated for the potassium rates. So we have 3 as well, 3 beta coefficients. In this case, the formula is just simplifying that to BJ or beta J. And then we have the alpha beta IJ component, which is calculating the effects of that interaction that we want to include in this model. So let's say if for some reason, if you had nitrogen and potassium, but for some reason you did not want to even bother about the interaction effect, you could have just not have this alpha beta in your model, which means it would not be in your ANOVA as well, and you would not even test for it. So it's normally you would include that interaction there, but I'm just highlighting if you did not want it in your model, you would not be in your ANOVA, you would not be able to test that effect. So really the effects model connects directly with your ANOVA table. Okay, so, this is just some notation that you're going to see on that ANOVA table, where N is the number of levels in nitrogen rate, which is 3, K in potassium rate, which is also 3, R is the number of replicates, which in this case is 4, and then uppercase N is the total number of observations or experimental units. And this, again, so if you have seen ANOVA tables before, which you probably have, the degrees of, so the assumption here is that each observation that you make on a experimental unit, so not subsampling. So let's say, again, on that example that we had, applying a treatment to the whole plot and then collecting 6 plants. Those 6 plants individually are subsampling, right? So there are different ways we can accommodate that within the analysis to make sure we have 1 observation per plot or experimental units. So the simplest one that people would do is basically take an average of those 6 plants, right? If you are analyzing them separately and you have 6 values for that plot, you would take an average and use that average value to represent that plot. That's one of the ways of doing this. You can also directly incorporate, another way would be to directly incorporate that data into the analysis, which we're not going to see today at least. But anyways, I guess what I'm trying to say is each observation that you take at the experimental unit level is considered to be independent from the others. And that is the assumption that's key here, and to understand that subsampling or not having subsampling. And each one of those independent observations you take at the experimental unit level gives you 1 degree of freedom near ANOVA. So it's like one piece of information you can extract from that observation. Because we do have 36 experimental units here, and we have 36 measures of yield, then we have 36 degrees of freedom total in our ANOVA table to use in different parts of it and learn about the treatment effects. So let's see that next year. Okay, so this was that ANOVA table that we already talked about. I do want to go through this again just to refresh your mind, because I will be asking you something after it, and I do want you to be thinking about it with me. Okay, so notice here that so on this ANOVA table, I removed the overall mean, but sometimes you would see an overall mean in there. I removed just because we're normally not interested in that overall mean if we're talking about ANOVA. We are if we're talking about regression, which is not the case here. So the way that removing that overall mean from this ANOVA table shows up is when we're calculating the total degrees of freedom, we do n-1. And this -1 here is because we are missing that overall mean from this table. So just so you can get some context here. So our total here then becomes 35 degrees of freedom. So now let's see how we are spending these degrees of freedom to learn about the data of this study here. So for each one of the, so we have the main effect of nitrogen, main effect of potassium, their interaction in the error term. Let's look at the degrees of freedom of each one of these sources here. So for each one of the main effects is basically, the formula is basically the number of levels of that effect minus 1. So for nitrogen, we have 3 levels minus 1. We have 2 degrees of freedom for this effect. The same thing for potassium. So main effects is just number of levels minus 1. That's your total degrees of freedom. This is something that you normally don't have to calculate yourself. You're going to get this as an output of the analysis. But again, you should know how it's being calculated so you can cross-check and make sure it is correct. Now, for the interaction is a little bit different because it's basically you multiply that by that. So multiply n-1 times k-1, and then you get 4 degrees of freedom. So here what I'm saying is to calculate the effect of nitrogen rate, I'm using 2 degrees of freedom. So I'm taking up 2 degrees of freedom from the total of 35 to calculate nitrogen effect. The same for potassium rate. And then for the interaction, I'm taking 4 degrees of freedom to calculate that effect. And in this case, everything that remains, so the difference between 35 and 4 plus 2 plus 2 is basically what goes into the error degrees of freedom. And this is going to be really important in a moment here. So just keep track of what we're doing. After that, we have our sum of the squares column. So I do not have the formula here. Sum of the squares is basically, it is a mathematical calculation that's trying to understand how much variability is being, how much of the total variability is being explained by each one of these components. So I just gave their names here. So sum of the squares of nitrogen, potassium, the interaction, and the error. So you can think of it as just understanding how much variability is being explained by each one of those factors in your ANOVA. Then next we do the mean squares, and the mean squares is where things start to be, where we need to start thinking about how things are getting connected. So notice how the mean squares for each one of these factors is basically going to be the sum of the squares of that factor divided by the degrees of freedom of that factor, right? So if you think about it, the mean squares is basically seeing how much information is being explained by the factor through the sum of the squares and dividing that by how many degrees of freedom you took to explain that variability, right? And it is still at the level of just that row. So this is sum of the squares of nitrogen divided by degrees of freedom of nitrogen, same for potassium, same for the interaction, and same for the error. So after we do this, then we calculate the F ratio, which is basically a division of the sum of the mean squares of that factor by the mean squares of the error. Now notice that the mean squares of the error is what is going on the denominator of the N rate ratio, F ratio, of the potassium rate ratio, F ratio, and also the interaction F ratio. So we're basically saying this error here is what I'm using to test each one of these effects in my ANOVA. This is going to become important in future designs. In this case here, we just have one error. There are going to be designs where we have different levels of errors. And that is really, really key to understand, to make sure that your ANOVA is using the proper error to test the proper effects. I'm not going to talk a lot about that today to not get you confused. But that's why I'm getting in very detailed discussion on this ANOVA table specifically. Okay, so there are, well, and then, so after we calculate the F ratio, so this number here, the smaller is this number, the less evidence you have that that effect is significant. The larger is this number, the more evidence you have that this effect is significant in your model, right? Because if you think about it, you're basically taking a number here, the mean squares of that effect, and dividing that by the mean squares of the error. Ideally, what we want is a lot of, or a very large mean square on top, meaning that you're explaining a lot of variability with your treatment, and a very small mean square of the error, meaning that you have very little noise that ended up in the error, right? So there are different ways of achieving this. One of them would be, making sure that you're treating your studies in a very meticulous way to make sure that you're not adding yourself extra noise to what is already a noisy system, like a biological system, right? So we're kind of thinking about that as far as, let's decrease how much sum of squares is actually going to the error by making sure I select plots that are homogeneous. I plan everything the same day. I apply all my treatments on the same day. So you're not adding extra noise that is not needed there. And so when you do that, so imagine you're dividing a very large number by a very small number. If you are able to achieve that, then your F ratio is going to be large. And then we use that F ratio and relate that to a T distribution to get a p-value. So I don't have a p-value here, but we're going to see that when we get to the actual hands-on exercise. So let's say if this F ratio here is very large, it means I have a lot of evidence. This p-value is going to be very low and have a lot of evidence that nitrogen rate has an effect. Okay, so let's just take a moment and think about some of these things. I want you in your head to make some connections, and then we're going to talk about it. What can I do to increase the chances of finding a significant effect? Or in other words, what can I do to increase my F ratio? Okay, so maybe let's keep the question. What can I do as a researcher to increase my F ratio and make sure I find significant effect? I want to go back to the ANOVA so you can take a look at it. So how can I increase this number? Any thoughts here? Even if you just think like mathematically, right? So if you have F equals 2 mean squares of nitrogen divided by mean squares of air, I want to increase F ratio. What should happen on the right-hand side of that equal sign for me to be able to increase it? Okay, so we have a few people here, so let's go in sequence. Okay, go ahead.
We have to correct the alpha level.
Okay, alpha level. So alpha level is going to come then on the next step, right? Where we actually define a level to compare that p-value against and determine if it's significant or not. But if we're thinking about this formula specifically, Pramod, you raise your hand.
Increasing the numerator.
Okay. So Pramod said increasing the numerator, decreasing the denominator. Let's go in that direction. But first, let me see. I had someone online said something.
Yes, sir. Mine was more of a question than an answer, I think. But like if you had more drastic rates and more variability in your rates, for example, would that change it if you like jumped up high, like with the
Yeah,
to higher numbers?
that's a really great, perhaps a little bit more philosophical approach, but it's definitely very important here because so Austin is saying, what if we had different rates? Like, so your treatment levels would be different. Would that have an effect? Most likely it would, right? So let's say we would like to select rates that answer our objectives. So if our objective here is to find for a response, a crop response, and I know that, let's say the optimum nitrogen level on average, let's say would be 150 kilos per hectare. So I want to have that level, but I want to have something lower and something higher than it, right? So I want to be in the space where I know the crop is going to respond to. It would make no sense that if I know the crop needs 150, if I come here and have my nitrogen rates as 0, 10, 20, it's probably not going to be a good selection of levels, right? I'm not going to see a difference there because it's such a small difference in rates that is way below what the crop needs. So it's going to be, everything is going to be probably the same as far as yield and on the lower side, right? So everything's going to have a low yield level. But that's a really great point, Austin, because that's going to also determine how much of a signal you have from your data, right? Which is going to say, so in that case, let's say we had a 0, 10, 20 kilos of per hectare in a crop like corn that responds a lot to nitrogen. You're probably going to have very little information being explained on your sum of squares of nitrogen, if that was the case. So that's a really good point, and is actually one that also comes into play here, right? But perhaps is not the one that I'm exactly thinking of, but it's a very important one in this overall conversation. But that would be something that we would determine when we're making decisions of the treatment design, right? But in this is probably especially something that plays a bigger role if you are doing something very new that no one has ever done, right? So you're like, okay, I have this new product. I mean, with fertilizers, we kind of know what are those levels, but let's say it's a new product, a biological product, and nobody knows how it behaves, and you're testing it, and we have some idea of the rates, so we may have like that rate, and then a little bit more, a little bit less. You do multiple studies, and everything comes back the same. Maybe you could increase your variability of treatment rates to see if that helps to find an effect. And then if you run that and it does, then you learn, okay, maybe the range of rates I need to have should be higher in this case. So that's a really important aspect as well. Okay, so Pramod was saying, so if I want to increase F ratio, I need to either or both increase my mean squares of the treatment or decrease my mean squares of the error. And that's correct. Now, perhaps we talked about, with Austin's comment, I think we talked about one way that we could increase the mean squares of the treatment, perhaps choosing levels that you're going to see an effect within the levels you choose. So that's one way. Now, how can we increase the mean square, or I'm sorry, how can we decrease the mean square of the error mathematically? Yes, Benita. Yes. Bingo. Yes. So Benita said increasing the, well, of what? Yes. So something that you're not seeing here is we do not have a line for replication, right? But we do, but that information is part of especially the degrees of freedom of the error. So this 4 here is the number of replications. So if we increase the number of replications, we're going to have more degrees of freedom going into the error, which is a great thing because the more degrees of freedom we have in the error, which is this component here, the smaller mean square error we're going to have, and the smaller mean square error we have is going to help us make this F ratio greater, right? So I hope you're making those connections and why more replications improve your power, and by power, I mean finding statistical difference in your treatments, right? And this becomes really important. So of course, we know that more reps you have, the better, but making this clear connection of why that matters mathematically is because of this reason. So yes, increasing replication helps. However, increasing replication of experimental units matter. Because sometimes what happens, I'm sure you've seen this or maybe had this in your research, is you think, well, I have this data table that I sample one plant per plot and I have, so 36 experimental units, 36 numbers. If I just go and sample 2 plants per plot, then I double that. So I have my replication or more replication right there. No, that's not the case. And that happens though. People do subsampling and assume that that is replication, which will increase their error degrees of freedom, but that is wrong because you're taking subsampling, which the concept of subsampling is taking more than one sample at the level of the experimental unit. And those 2 samples are not independent because they belong to the same experimental unit. And because they're not independent, you cannot treat them as a true rep because they are dependent. And that's one of the assumptions they know. So if you come here and you think about it, let me try to improve the power of this analysis by increasing my subsampling. You're thinking the wrong direction. The only way that subsampling really helps you is that, so let's say you sample 6 plants and you take the average of those 6 plants. The average of those 6 plants is something you can use here, right? So it is going to be a true replicate. So it should contribute with 1 degree of freedom to your analysis. And the only way that's going to help you is that it's going to make that value for that plot a little bit more constant, right? So let's say if you sample 1 plant and you end up sampling a plant that is not representative of that plot, that value is just 1 value, but is going to have more variability in your analysis afterwards. But if you go and you sample 6 plants and you take the average of those 6 plants, that value you're using for that plot is a little bit more certain of the true effect of, or the true condition of that plot. So it helps you there to stabilize that mean, which is, it could be good. However, a better thing that could be done where you truly can increase your error degrees of freedom is just to have more true replicates, right? So instead of having 4 blocks or 4 reps, have 5 or 6 or 10. That is going to give you more independent observations that do go into your error degrees of freedom and do make your study more powerful, right? So it's better to have, let's think about this. So if you have 4 reps, and you take 2 subsamples of each one of your 36 experimental units, it is better to instead take even just 1 sample of each experimental unit and double your number of reps. Maybe your work is going to be the same. Of course, you're going to need more area because now you're having more blocks and reps in this area, but that will truly give you more power when it comes to the analysis, which is what matters. Yes.
This more like if so this at the farm level, it's CRD design, and like consider that you have 300 feet of long row. If we take like it will be still considered as subsamples, or we can treat them as a reps. So
I
if,
don't
like,
think
there
I
is a
follow the
300
question.
feet, like long
Mhm.
strip,
Okay,
and we take sample from 3 samples, each from 100 feet difference.
okay.
So should we consider that as a subsample, or there could be variability too?
Okay, so if I understand your question, the concept of if you're taking a true sample or a subsample should come from the concept of what is your experimental unit, which is connected to how you apply the treatments. So if you did apply, if your plot is 300 feet in size and you did randomize to plots of that size and you did apply your treatment to that whole plot, then that's your plot, right? So if you take 3 samples within your plot, that is subsample. However, if you were to instead do plots of 100 feet size and still randomize everything to that level and then apply treatments differently to each one of them according to your randomization, then your plot is 100 feet. So if you take those same 3 samples across this strip that now has 3 different randomized treatments, each one would be a sample. Any other questions or thoughts around this? Okay, so I'm going to go back to the slide that I had forward, or I had shown after the ANOVA table. So we can have more variability explained by treatment, right? Which is going to either increase your, or is going to increase your sum of squares and potentially your mean squares of that treatment. And that goes back to Austin's comment. And that was a really great comment, Austin, because I guess I had not thought of an example like what you described. So I appreciate you bringing that up. Or having less variability explained by the error, right? Which could be, so we really talked about increasing replication increasing replication of true replication, not subsampling. And that has an effect on the degrees of freedom of that model of the error, which is the main way that we can really increase our power. But of course, if you have less variability explained by the error itself, can also help you. So let's say, you know, if you have this study and you have, I don't know, an undergraduate working in your lab that never worked with research, and you just give them a protocol and say, go have fun. You know, they may do a lot of mistakes because they're not trained yet that could increase the variability of your error, which has nothing to do with degrees of freedom itself. It's just that maybe, you know, they did something to one rep that he or she did differently on the other one, and that is just adding extra noise that is going to your error, right? So by being, I guess, more meticulous with what you do for the whole study helps you to decrease that how much variability is going to there in the first place. So less noise in the error or more degrees of freedom with the error, which is really the key one here. Okay, so this is just a keeping up with our motivation example. We're gonna be working with this data, so we're gonna see again this ANOVA table when it comes to the exercise we'll do next. But we see here that there's this intercept, which again is, we can think of this as the overall mean, which is in our effects model, and R is gonna give you this row on the ANOVA table. So that's what it is. We see that here it has a very large sum of squares, so a lot of variability being explained by that overall mean. We have the degrees of freedom here, the F value, and then finally the P value, which is relating this F value to an F or T distribution. So the larger is the F value, the lower is going to be your P value. Then we have the effect of nitrogen, so sum of squares, we have 2 degrees of freedom. Here's the F value, here's the P value. The same for potassium rate, the same for the interaction, and finally for here in R, it's called residuals, but this is the error term, right? So again, this error term here, so the mean square, so we don't have a mean square column in this ANOVA table coming from R, but that mean square of the error is what is being used to test the effect of each one of the other effects. So very interestingly, you can see that how much variability is in the error is actually equivalent to what's in or about, you know, almost equivalent to how much variability is in that interaction. Potassium rate has very little variability being explained by it, and so on. So we see that there is a lot of noise in this data set here, in this analysis. Okay, so you know, we normally choose an alpha value to compare to this p value and say if these effects are significant or not. A alpha value of 5% or 0.05 is the most common one. If we were to use that to compare here, what would be considered significant in this ANOVA? The interaction, right? Yeah, and also the overall mean, but we don't really care about that in an ANOVA setting. And I guess before this next point here, I just want to tell something that you should always keep in mind. So whenever we have analysis of variance that include interaction terms, the way that we make a decision on how to continue the analysis after this point is beginning of the interaction terms, right? So let's hypothesize here that everything was significant. So interaction and main effects. So this is the interaction, the main effects are N rate by itself and potassium rate by itself. So if everything was significant, including the interaction, we should only look at the interaction effect. Because if the interaction is significant, it's telling you that if you look at the main effects alone, they're not gonna tell you the whole story, right? You're gonna be missing something. So even in this case, the main effects were not significant, but even if they were, I mean, it's still okay for you to extract means and do pairwise comparisons and show that, but it should not really be making inference on that because the main effects in this case are not telling the whole story because the interaction is significant. So always begin by the bottom of the ANOVA table and going up, right? Especially if you have, in this way, is a two-way ANOVA. So we have two factors interacting. Sometimes we may have 3, 4, I've seen 5. So that starts getting really complex, right? So we always start at the most complex interaction, which normally sits at the bottom of the ANOVA table, and make our way up, making sure that if something is significant, if some interaction is significant, you look at those effects in that interaction and not alone. That will make sure you're learning properly from what the data and model are telling you. Okay, so we have this ANOVA table. We know what's significant. So next thing is we should go ahead and extract means, do pairwise comparisons of the interaction term. However, before we do that, we need to check that this model is appropriate for this data. And on an ANOVA setting, we're going to see how to do that and what metrics we're going to be using for that. And this, perhaps in an ANOVA, is a little bit more difficult to create some really good examples of how bad a model can be to a data. But when we get to regression, that's going to become a little bit easier to visualize. Anyways, let's go and start talking about residuals of this model, the assumptions that we're checking, and so on. And something to make very clear is we need to check the model assumptions that are based on the residuals. We're going to talk about what's residual in the next slide here, and I make a point about that as well. So the linear model residual is basically that error term. If you remember our cells model, right, we have overall mean, effect of nitrogen, effect of potassium, interaction, and this EIJK component, which is basically what's left, the information left after you account for all those other effects, right? So this is what I cannot explain in my model goes into the error term. So the residual of the model is basically the value of that observation minus the predicted value for that observation. Because now imagine you have the data point you collected, that you observed, and you have what your ANOVA model is predicting for that value to be. There is a difference between these two values, and that difference is the residual. And this residual is really based on that our assumptions of the linear model should be tested. So really, in other words, the residual is a difference between your observed data, so what you collected, your yield point that you measured, minus what the model is predicting it to be. I have a plot here that I want to perhaps use to demonstrate what's going on. So here we have treatments. So we have all of our 9 treatments, even though, it's going from 1 to 11, but we have nine points on the x-axis. And then we have yield for each one of those treatments. What we see here in purple are the true observations. Okay, so that's what I truly measured. The blue line is the overall mean of this data. So you can kind of think of this as that mu component on the effects model. So this is our overall mean. And then the green squares are the mean of each one of these treatments. So the residual for each one of the observations would really be the distance between the point and the treatment mean. So this distance here is what's left, what the model cannot explain, right? Because if the model is giving you a prediction for the treatment mean, it is giving you the green dots. But as you can see, there is a spread of the treatments around that green dot that the model cannot explain. That's the residual, that's the error that's going into that EIJK component. So these differences here, so let's say any data point that's lower than the mean is going to have a negative residual value. Any data point that's above the mean is going to have a positive residual value, right? So these differences here between the point that we observed and what the model is predicting, which is the treatment mean, is what we call residual. Okay, so you may have seen this notation already, but this basically summarizes the assumptions of the linear model that we have to test. So EIJK, so the error of each individual observation, which again is related to the true value minus what the model is predicting for that to be, is independently and identically distributed normal. This is what IIDN means, with a mean of 0 and a standard and a variance of variance square or standard deviation of sigma square. Where each one is residual, so each observation has a residual, right? So this is basically sums up the assumptions, and let's break that down into something less mathematical and more, I guess, put that in words, really. So the random experimental errors or the residuals are assumed to be mutually independent. This is something, how do we make sure that this is true? Is basically by doing randomization. Randomization is what gives you the assumption that you can make about observations being mutually independent. If you do not have randomization, for example, we're going to talk about this in class in a later lecture. If you have repeated measures, in brief, repeated measures is whenever you measure something that cannot be randomized. For example, I can totally randomize my treatments here, but let's say that I also want to measure the effect of time. Like I measure something, I measure plant height, maybe 30 days after planting, I measure plant height 60 days after planting. So now I want to see if there is an effect of days after planting on plant height, which probably would have. But I want to have that in my model. So I want my effects model to have, so instead of N, K, and interaction, it could be, nitrogen days after planting interaction. Could be that. I want to test the effect of nitrogen on plant height over time. Now, the issue with that is nitrogen and potassium I can randomize, right? And therefore, I can make the assumption of independence. I cannot randomize time. I cannot say that 60 days come first and then 30 days. I cannot do that. We cannot randomize time. We cannot randomize space. Anytime we cannot randomize something, we're basically breaking the assumption of independence. And there are ways around it. We're not going to talk about that today, but I just want to, again, make this point that randomizing gives us the chance of assuming that our observations are independent, and therefore our residuals are independent. So we're going to also test that these residuals are normally distributed with mean 0 and common homogeneous variance of sigma square across all treatments. And also that we do not have extreme observations, which is related to the normally distributed assumption as well. And we're going to see why that's the case. Okay, so this formula here that the formula on the previous slide is the formula for the raw residuals, which can be used to check most of the assumptions. However, there are other types of residuals. There's like different ways of standardizing residuals. I want to show you one of them here, which is what we're going to be using, that is called a studentized residual. So basically, the studentized residual is gonna, well, let me take one step back here and talk about this. So raw residuals, they're useful to test most of the assumptions except the one of outliers. And I don't know if I have an example of that here, but if you have a raw residual, it means that the magnitude of the residual is going to be the same as the magnitude of your response variable. So if you're measuring yield in kilograms and you have, 10,000 kilograms as kind of like your magnitude, then your residuals are going to be on that scale. If you're measuring concentration and is ranging from 0.1 to, 0.5, then your residuals are going to be in that magnitude, right? The magnitude of your response variable is going to impact the magnitude of the raw residuals, which does not help us to identify outliers. So we need to standardize this to a common scale that follows a normal distribution centered on 0 to be able to identify outliers. So in that case, for outliers, raw residuals are not useful. Then we need to standardize somehow, and studentized residuals are one way of doing that. So studentized residual is basically the raw residual divided by their standard deviation. This is just a formula. Basically you see that. So this is the studentized, this is the raw residual divided by its mean square error and some extra math there. I just wanted to show the formula, even though in R, this is just a simple line of code that we don't have to worry about the math. There is a function that does that for us. Now, once we standardize the residuals, we can use the central limit theorem and make this assumption that if now our distribution of the residuals is centered on 0, we can assume that if they're coming from a normal distribution, then 95% of those residuals would be within plus or minus 2 standard deviations, and 99% within plus or minus 3 standard deviations. Now, I'm highlighting 3 standard deviations here because that's the threshold that's normally used to determine if a residual is outlier or not, especially a normalized residual, in this case, a studentized residual, because then we have those thresholds of 3 very clearly, regardless of the magnitude of a response variable. Okay, so a very key point here, and I think, as you are writing your papers, reviewing other people's papers, you're going to see some of this. Valid analysis depend on valid assumptions. If the model assumptions are not met, then inference based on that model is meaningless. That model is not a good fit to your data, and therefore you should not use it to make inference, statistical inference using this model. Your data is not going to change, right? You collect your data, it's there. The model, however, can change. So here we're fitting a model that fits the design that we had. But if your assumptions are not met, there are different things you can do to your model to help it be a better model to your data in a way that you have residuals that are good. Remember, your data is not changing, but your model can change. And if your model changes, your residuals change. Your raw data doesn't change. Your residuals depend on the data and the model. And this is another thing that I see a lot is a lot of papers, people are saying, we checked that the raw data was normally distributed. Okay, maybe that can be helpful sometimes, but that is not an assumption of the linear model. The linear model assumptions are based on residuals and not raw data. And again, because raw data remains the same, residuals change if you change the model. So assumptions are based on residuals and not raw data. If your assumptions do not hold for a given model and data, then the validity and repeatability of the results is questionable. Because now, again, you do not have a good model for that data, and therefore learning about that model is not going to be useful in that case. Always check your residuals and their assumptions before making inference. Because if something is actually wrong with those assumptions, we're going to need to fix that before you can use this model. Okay, so if you check assumptions and they don't hold, do not use the model for inference. Do not extract means. Do not do pairwise comparison. Do not do anything else with this model, because basically what you're doing is not going to be, those results are not valid. Okay, so let's talk about how do we check these assumptions. So here, the first one I'm bringing up is the residual independence. So what we have here for this type of assumption, what we use to check this is we plot the fitted value. So the fitted value, let me try to think if I can. So this is ANOVA, so this is not regression, but I think thinking in a regression format maybe, well, you know what? Let me take a step back and change what I was going to say. If we think back again to that plot that I showed you with the overall mean and the green squares showing the mean, the fitted value in that case would be the treatment mean coming from the model, which was that green dot. So that is what the fitted model or what the fitted value is. And then this on the y-axis, so the fitted model is what we have on the x-axis. On the y-axis, we have the studentized residual. So it's the residual, the difference of the observation from the treatment mean, divided by the mean square error of the residuals to make that a studentized. So that's what we have on the y-axis here. This is a very common, popular plot to check many of the assumptions that we're going to be checking here. So talking about residual independence first, what we do want to see here on the residual independence is that the data points here that are our actual residuals, so the purple points here, we want to see them just kind of like randomly scattered, right? We don't want to see a fixed pattern in these residuals. A visual way of assessing that is, I don't know if you've been using ggplot enough to, if you have, maybe you're noticing this, but this blue line is a geom smooth line that basically fits a smooth type of regression on your data points. If your assumption of independence holds, you would hope that that smooth line that ggplot is adding to you would be right on top of the 0 line. Remember, so the assumption here is that your residuals are normally distributed with a mean 0, so that it sits on 0. And even if it doesn't, I mean, it can wiggly around it, but you would wish that your error bands of that blue line at least comprise 0 across the x-axis. So that's like a visual way of assessing this. So I'm not seeing any clear patterns in the residual, and by that I can assume independence. Also because I know this study was randomized. If this study had not been randomized, maybe just having this would not be enough, because again, randomization is what gives us the strong assumption of independence. So no clear pattern here, evidenced by that geom smooth. I would say residual independence, check. The next one is residual homoscedasticity. So that's a word that doesn't come easily out of the mouth, but really what that means is, so the assumption again being that residuals are normally distributed with a mean 0 and a variance of sigma square. It means that, again, we want to see a shotgun effect here. We don't want to see any clear patterns. And normally if you have a lack of homogeneity, or if you have heteroscedasticity, one way that this a lot of times shows up is your residuals look like a fan shape, like this. So on the lower sides of theta value, your residuals are small. And as you increase your theta value on the x-axis, your residuals increase. This is very common in some types of studies. I worked with nitrous oxide emissions in my master's, and that is something very common in that type of research. If you have that, you should fix that before you use this model for inference. And just a point here is that linear model assumptions, so the big ones being normally distributed and homogeneous variance, the model is more robust against lack of normality. So let's say your residuals are not quite normal, they're a little bit skewed. If it's not very, very skewed, the model is still valid most times. But the linear model is the least robust when you have heteroscedasticity. So if you do have heteroscedasticity, that is the main issue that you're going to have to fix before using this model. And this is one way of checking that, is that your residuals are spread like that you don't have like residuals with very small variance in one part of this plot and very large variance in another part of this plot. So again, for this case here, data is spread evenly and centered around 0. Again, evidenced by that geom smooth to help us to have a visual understanding. So I would say this looks good to me. The next one is the assumption of residual normality. There are a couple of different plots that we can use for that. The legend here is, or the text size is a little bit small, but let me just zoom in so we can see. The first one is called a quantile plot, or also QQ plot for short, where it has on the x-axis the theoretical quantile. So if your data were truly normally distributed, that's what the theoretical quantile is, and then plots your actual sample quantile, which is coming from your data points. What we do want to see is that, so, and then each purple point is one of your residuals from your model. So what we would like to see is all of these points sitting right on top of that black line, or at least very close to it. In this case, we have some points on the tails. So these points and these points that are not really on top of that line. But I wouldn't be too worried about this, because even though they're off, they're not terribly off. Sometimes when this plot shows a lack of agreement or a lack of assumption being held, it would be like you would have your points in the middle, right on top of the line, but then your tails are gonna be really off. Like sometimes it's almost like an S shape, the way that it looks like. So this is not terribly bad. Another one that we also use to check residual normality is it could be a histogram, it could be a box plot. I'm showing a density plot, which I think helps to visualize this. So basically we have the studentized residuals right here, and then the density of those plots are just the frequency that they appear under this distribution. So it looks like, I mean, it's not a perfect normal distribution as you would have like a bell shape, but it is centered on around 0. So we see here the peak is very close to 0. And I guess, it does have a little bit of some heavier tails here that the normal distribution would not have, but it's not terrible again. Like I would say it looks, it looks pretty good at this point as well. So as far as residual normality, it's common to have some points on the tails that don't look as good, but also the fact that we have a low total number of observations also plays into that, right? So if you have a low N, I wouldn't be super concerned unless you have like really, really bad skewness on the tails, which is not our case. And then the last one is residual outliers. So as you can see, this is the third time I'm showing the same plot to check different assumptions. Again, this is a very useful plot for that. Now on the residual outliers, this is really where using a normalized residual, in our case, the studentized residual, makes a difference. Because now, basically, we have not talked yet about this, but it has been in every time I showed you this plot, we have these red lines here, horizontal red lines, that are sitting at 3 and -3. So those are your visual cues to identify outliers. In this case here, all of our data points are within 3 and -3. I don't have anything going more than 3 or less than -3. And again, we can use these thresholds because we're using studentized residuals and assuming they're normal, and under the normal distribution, you would assume 99% of your data to be within ±3 standard deviations, which is what we're showing on the 3 and -3 in this case. So that's where the 3 ±3 standard deviations come into play when finding about outliers in this case. I guess when I wrote this slide here, I was looking at a different model. And that's why I wrote that a couple residuals were beyond -3 and 3, which is actually not the case with this plot. So you can just ignore this comment and everything is within that range. So we should be good here. So that assumption holds as well. Okay, so there are other assumptions that we can keep going like for longer, but these are the main ones that I would use, that I use every time. And so after checking these, we confirmed that our residuals are independent, right? We did not see any clear pattern. It was like a shotgun effect. It was a cloud of points, independent residuals. Also independent because of that, associated with the fact that we randomize the study, gives us peace of mind that they were independent. They were homoscedastic, so they had homogeneous variance. Again, the same plot, it just means that we did not see increasing values of residuals like a fan shape. It was everything evenly scattered in that plot. They were normally distributed as we checked on the QQ plot and also the density plots. And also we did not see any outliers. So I just want to talk a little bit about something here. So this course, we could have a whole course showing you messy data and how to fix it, right? This is not the goal of this course. At least, we can talk about some of these quickly here just to give you some help. But if you do run these on your data and you don't check the boxes, I'm sure there are different courses at UGA that will spend a whole semester just talking about that. If you don't have time for taking a course, you can shoot me an email. I can send you some resources that I have that can help you. There are some books out there. There's some other resources online. But I just want to make a quick note here about outliers, because that is perhaps the easiest one that you can have an impact without having to take a course. So outliers is something that, especially in design statistics, it is not advised that, let's say I look at this plot here and I have one of these points that is like -4. in that sensitized residual y-axis. So -4 would definitely be considered an outlier. However, if that happens, you should not simply go to your data, see what data point is causing that to be a -4 sensitized residual and delete it. That is not recommended, it's not advisable. And if you do that and you say that you did it in a paper, you're probably not going to get published because that is not good statistical, I guess, approach to solve this issue. The first thing that we do say about outliers is if you do have an outlier, go back to your data and make sure you know which point is causing that outlier to be created, to be such an outlier, and just investigate a little bit more. Because sometimes outliers can come from perhaps erroneous data entry. Maybe you were entering your yield and then instead of saying 10,000, you said 10, right? And then that's going to be a huge outlier on your residual plots. It could be data entry error. Maybe it was a machine error. Maybe, you know, when you were harvesting the plots, I don't know, maybe something happened, maybe something broke in the combine, or I don't know, maybe the person that was supposed to take 6 plants took only 1. You know, it could be something that happened on the field like that as well. Another times, you know, so it could be something that happens on the field. It could be something that happens in the lab. Perhaps you're doing an analysis then on whatever you brought from the field, and then you find out that, you know, a concentration reported by the machine was wrong, or something happened with the machine. So if you can trace back what caused that data point to be so abnormal, then it is okay to delete, because you know that point is only that abnormal because this specific thing happened. In that case, yes, you can go ahead and delete that point and let the model take care of that missing data itself. It is not okay though for you to go back, make sure you check all these boxes and saying, was it a field error? Was it an equipment error? Was it a data entry error? And you did not find any of those, and you still just go ahead and delete it. That is not really good practice, and it is discouraged. Because what happens is perhaps that data point being such an outlier. So let's say you had a yield data point that was, you know, a lot higher than the rest of the field, but still biologically possible, still within within reason. Maybe there's something about that part of the field that did it, and it's just a possibility of that data point of yield in that field being that high. And so you don't want to just remove data because it doesn't fit your model. You know, you should remove if you do have reasons to believe that's not a truthful data point. So just wanted to make that parenthesis here. So if you come here and check all these boxes, at this point, you can say, okay, I trust my model. It is representing well my data. Now let's use it for inference. So in summary, you know, CRD, we use that, and by using it, we're randomizing without restrictions. Each term of that effects model has a row in the ANOVA table. We talked about raw and sensitized residuals. We specify here that if your model assumptions are not met, inference is meaningless and you should not do it. You should fix your model first before, and then recheck your residuals until they are matching or fulfilling the assumptions. We talk about the assumptions, which in a nutshell would be what this formula here says. So they're independently and identically distributed and normal with a mean of 0 and a standard deviation of sigma square. And that's it. So that's what I had for the lecture part of today. Now the next step is I want us to walk through the actual exercise that's going to have us using real data, real coding, and then develop this analysis in R. Before we jump into that, any questions? Okay. Online, any questions? All right, I don't hear anything. So let's do this. I just pushed to GitHub earlier this morning the script that we're going to be working with. So if you go, I just want to show you first on GitHub. So there is a new script and also a new data set. So the 03 data folder now has a wheat nk bulk.csv data set. And the 04 class code folder has a 0201 CRD partial.qmd. I'm assuming for this class that you were all able to get your Git and GitHub connected and working properly. If that is the case, the way that you would retrieve these would be to open, when you did a fork of this on your computer, it would probably look like something like this. And in your case, I think you have on our studio project in this folder here. So if you do have that, you would basically, I don't have on my side because I did not fork it. This is the original one in my computer. But in your side, I believe you have. If someone can confirm that you do.
Yeah,
Okay.
it's been pulled.
So if you do have an RStudio project icon on this level, you basically just launch that. So that's going to launch a different RStudio project, remember. That is not going to be the same as mine. I have pulled up here the 03 CRD. It's not the one that you're going to have. You're going to have the one for that 2024 underscore DSA. On your Git pane or panel, you're going to click on this button here, which does a Git pull. So remember, the Git pull is what's going to bring updates from GitHub to your local computer. So if you, once you click on that Git pull, you should be able to see on your files tab, if you navigate to those folders, you should be able to see the data and the script there. So before we go further, I just want to take a moment here and allow you all the time to do this, especially because the first time we're doing this, I do want to give you some time to figure that out. So I'm just, just going to repeat the steps again. So you don't have to go to GitHub, right? The only thing that I showed you that on GitHub, but the only thing that you need to do would be to come so I'm assuming you were able to fork and clone the 2024 DSA and move that into the class, the main folder for this class. Then if you did, you would go inside 2024 DSA and you would probably have an RStudio project icon in here. So you would double click on that to launch the RStudio project. I don't have on my side, but you should have on yours. So that would launch a 2024 underscore DSA RStudio project. Which again, I don't have, but you would. And once you're there, you go on the Git panel here, and then you click Git this button to do a Git pull. Okay, I'm seeing some confused faces. Let's see, who was able to do it? Okay,
I was able to do it, Dr. Bastos.
awesome. Thanks, Austin. So if you were not able to do it for some reason related to your Git or GitHub, for sake of time, I would say go ahead and do the manual way for now. Go on GitHub, download it, unzip it, and so on. I don't want that to be what we keep doing, right? So if you were not able to do this in class now, let's troubleshoot that and make sure that you can in future exercises. But just so you can follow along the exercise, if you were not able to Git pull, do that manually as we've been doing in the past, so you can follow along, and then let's touch base later to fix whatever is going on. Okay, so if you were able to do the Git pull, or if you're doing manually by downloading from GitHub, going GitHub, download, unzipping, all that we've done in the past. Now, if you go back to your folder structure in your computer, you should see, if you go inside 03 data, you're going to have that wheat underscore NK underscore bulk as a data set there. You can copy that. So remember, even though you're pulling from GitHub directly, but we're still moving this to the appropriate project, that folder that we're using, which is 03 CRD, right? So we need to copy this data from what you pull from GitHub on the 2024 DSA folder and paste that inside of the 03 underscore CRD folder that we have already created last class. And I guess, let me think about it. So last class, so remember that the 03 CRD, we created first on GitHub, and then we cloned that to your computers. So you should have a 03 CRD that first started on your personal GitHub account, that we cloned that to your computer. And I think we stopped at this point, or I think we stopped at just cloning. So maybe you don't have yet the code data and output on your computers, which, yeah, I think that's what we did. So please go ahead and create the code data and output folders on this 03 CRD. And then from the 2024 DSA, I want you to copy that wheat CSV data inside of your data of 03 CRD. And the same thing with the script. So if you go back to the 2024 DSA, there's going to be in that 04 class code, there's going to be a partial script for CRD. I want you to copy that and then get outside of that folder, go back to your 03 CRD and paste that inside of code. So here's what I want to do. If I want to allow you 5-minute break, just so you can stretch, get some water, go to the restroom if you need to, and then we'll come back at 10:47. So 5-minute break. If you were not able to move the files properly, let me know and let's work on that within these 5 minutes. But if you are able to, then enjoy the break.
But after this,
Okay, so let's get started with the hands-on exercise. I am assuming that, let me navigate to that, to my folder so you can see. So this is how my folder for this course looks like right now. What I'm assuming that you were able to do to be able to follow along is on your 03_CRD folder. If you go in there, you know, we have the code, the data, and the output folders there. We also have the RProj icon right there. I want to invite you to launch RStudio by clicking that RProj button. In my case, it's already launched, so I'm just going to pull it up here so you can see. So this is also a Git and GitHub repo. If you remember from when we were working on that exercise, you first created the 03CRD on your personal GitHub account, and then you clone that into your computer, meaning that everything you do in your computer right now has the potential of being tracked and traced with GitHub. Of course, you have to ask for it to do those steps, but it's going to be able to do it for you. And then if you do a git push, anything you do here is going to go to your GitHub. So maybe let's just do a quick check first. So if I come here on my files tab, I click that R blue button to go to the main folder structure of this project. You should see on your, if you click on the code folder, I have more stuff than you do, but you should see your 0201 CRD partial. And if you go back again to the main folder, clicking the R's blue button, and you click on data, you should see the wheat and NK bulk.csv. If you were able to, yes.
That will be after we copy and paste it into our folders in the file explorer.
That's right, yeah.
When we pull it from GitHub, after I pull it, it's visible. That means I go to my file explorer and then copy it.
Yes, yes, and let me just I guess rephrase what you said, just so everyone is on the same page. So the 2024 DSA is what you made a fork and clone, right? So you have a copy of that on your computer now, that whenever I share new files, data, and code, instead of you going to GitHub and downloading it, you can just go to your computer, launch that project, and do a git pull. That's going to bring all the changes to your computer. Now, however, you have another Git and GitHub repo that is your own for this project of 03CRD, that now once you do a git pull on the DSA, 2024 DSA, you copy those files manually from those folders to the 03CRD project, right? So you still need to, you do a git pull and you still need to move them to your folder. That's the one that you're going to be editing, right? Remember that I don't want you to be editing the files from inside the 2024 DSA folder. That's just the way that you retrieve the files, but then you copy them and paste into your true working project folder. You know, something that I just want us all to do here is so after you have moved your files, so the data and the script from the 2024 DSA to the 03CRD, and you have the 03CRD project open, which you can check on the top right, let's do a stage, commit, and push. So basically what changed now is that you brought these files into this project, right? And that is on your local computer. You may have not asked Git on your local computer to track them. So let's ask your local computer to track them, and then let's also push those changes to your GitHub, right? So this is your GitHub. So I'm not sure what you're seeing on your stage. It may be different from mine, but you can just click on everything in stage, everything that's needed. After you click, so that has done a stage for you. So now we can click on the commit button, which is that one right there. you can, now we're doing more stuff here, so you can kind of see how it is changing, is showing you below everything that was changed. So everything that's green is a addition, everything that is in red is a deletion. Since we did not delete anything, we just added new things, everything is green. So now you can come on your commit message and say something like, I don't know, starting CRD project or exercise, something like that. So you can write that message and then you can click on commit. I'm not gonna do that on my side because, well, let me do that on my side as well. I think it would not create issues. So let's say creating CRD or starting, right? Starting CRD exercise. And then we click on commit. Then it's doing some stuff behind the scenes. Once it stops running, then you're good to go. Can close this window. And now, right from here, we can just click on that push button, right? So let's push this to GitHub. And I think that worked all right. If it didn't give you any errors, which I don't expect to have happened, then it should have been right. So if you close this and you close the commit window, and if you just want to quickly check that on your GitHub. So let's say you're going to be github.com, and then it's going to be your user / your username, right? So mine is Leo M. Bastos. And then the repo is called 03_CRD. So it'll be github.com / your username / the repo name, which is 03CRD. If you cannot find that path, you can just go to your GitHub as well and just navigate by clicking, right? So GitHub, I would have the repos here. I'm just going to search for 03CRD. It is right here. And then I can see that my commits that I did on my computer are showing up on GitHub, right? So now I have that data folder showing up. I have this data. In my case, I have more stuff than you do, but you're going to have that one data file showing up, and you're also going to see that one script showing up on GitHub. So something I will try to remember myself, but if I forget, please help me to remember this. I do want us that at the end of today's class, we're not going to finish today the coding exercise for this, but at the end of today's class, I do want to ask you to do the same steps. You do a git stage, or you stage your files, you commit them, and you push them. Because that way, every time that you work in class or even after class on a coding project, you're taking a snapshot of the difference. So right now, we took a snapshot, right? So we know how these files look like at stage 0. Now, as we start developing these, I want you to take commits at the end of the class. So stage, commit, and push. So everything you do in a class is represented in a commit on GitHub. So if you want to say, for some reason you want to go back to how your files look like, at the beginning of a class, you can use your Git history to do that, right? So it keeps track of what you're working on each class period. All right. So let me close this, go back to our 03CRD project. I want to invite you to launch your script. So the code, in your case, you just have one. So go ahead and launch that on your RStudio. Let me increase my font size here. A quick tip that I would imagine you may have become familiarized already is that if you are not seeing the table of contents or the outline here, if you're not seeing it, it's going to help you if you can see it, because it's going to help you understand in what part of this script we are at any given stage. Okay. Let me ask you this. Was someone not able to have in front of you exactly what I have in front of me? If someone was not able to move all the files around and get in the right place. Yes, Usman.
I'm missing that project file. I think I have missed some step, so I'm not unable to see the code in my folder.
Okay. Were you able to fork and clone the 2024 DSA?
Yeah.
Okay, so you did that. So if you did that, did you did the git pull?
Yeah.
Okay, so you have the files already in your computer, just in a different folder?
Yeah.
Yeah, so it's just a matter of you moving them from that folder to the 03 CRD folder. So let me just show you. So the 03 CRD should have you, this is something that you create on your side. The code, data, and output folders is something you create. And then you just move those files over. Do you have an R project on that 03 CRD?
Yes.
Okay. Yeah, so if you have an R project there, then I guess you just need to move the files into this folder and then it should be good. So I have some introduction to the topic here. So I'm gonna get started with that. If at the end of that, you don't have it ready, let me know.
Yes.
Okay, so this script here, the goal that I have with this script is that we create this analytical workflow for a completely randomized design that begins with importing data and ends in making a publication-ready plot. Okay, and every step in between. And there are many steps in between. You can kind of see them separated by letters on this table of contents on the right, but there are many steps, and we're going to walk through each one of them. You know, in a way that you will be able to understand what they are. Also, we're going to talk about some things here that I found make a difference. Sometimes, some of them make a difference every time, that I don't think a lot of people really get into this topic, which is what type of contrast we're using. And if you don't know what I mean, don't worry, but we're going to talk about this when we get there. What type of some of the squares we're using when we run ANOVAs. And also deciding how to extract and display model means and pairwise comparisons, especially when you have interactions. This is something that, you know, I kind of came across this as one thing that I wasn't sure how to handle at some point, and I don't think I really was exposed to this in my stats courses, and it's something that makes a difference both on your side, on how you make this decision, but also how you plot this data and how you create the intuition of your audience to understand what you're showing. Anyways, you know, right now that's kind of up in the air. I guess it's not, I was not very clear, but we were gonna get to those points and then talk about them. All right, so, you know, in every script, also my goal here is to show this workflow. So this workflow here is something that I think a lot of people kind of know that these steps are important and then kind of do in some way or another. But I never found a resource that said, here, this is a workflow that you can take this script and apply basically to any statistical analysis, especially experimental design. Of course, you're going to have to change your data. Maybe the wrangling steps will be different. Maybe the model is going to be different. But the workflow is very similar. For me, I use the same workflow for every analysis. So I want to expose you to this workflow as well. And part of that workflow, as in every script that at least I develop, and most of the ones you see online as well, people, the first thing they do is they load their libraries, their packages. So if you were just to hit the play button here, you may get some issues because I don't remember if I asked you to install Broom, EMEans, and multi-comp. If I did not ask you to install, and if you have not installed this outside of this class, you're going to have to install those packages. I left you there that install the packages function for the Broom package. You can go ahead and install it. I am assuming that these should be very straightforward. I don't think anyone's going to have a lot of issues installing them, but if you do have issues, let me know. So you want to install Broom. After that's done, you want to install EMEans. And after that's done, you want to install multi-comp. Perhaps, I know that multi-comp, even though we install multi-comp, there's also a package called multi-comp view, which if I remember well, it installed along with multi-comp, but if it's not, you need to install it. It's called multi-comp view. A refresher here is that install packages, we only run once for that package, right? So once you run line by line. So don't run the whole chunk when you have a lot of install packages, because if you do have an issue with one of them, it's going to be more difficult to know which one it was. So have your cursor in one of the lines and just run that line of code first with command return or control enter. If it goes through, goes to the next one and so on. Once you install all of them, you can either delete all the install packages, or if you prefer, you can just comment it off with adding a hashtag in front of it. So R does not try to run them when you render this file or if you run the whole chunk. Okay. Assuming that you were all able to install these successfully, let's just go ahead and load the packages. And just a refresher, so tidyverse is a package that actually has multiple other packages inside of it, that they're all part of the tidy family of packages developed by RStudio. So these include dflyer, tidyr, ggplot2, which we have been using a lot in this course already, but others that we have not used that we will in the future. So instead of asking to load each one of those packages individually, I just ask to load tidyverse. This package car here, oh, I don't think you have car either. So if you don't, please go ahead and install car just like we did above. So this package car has one function that's useful for us, and it's an ANOVA function. When we get to that, I'm going to talk more about it, but it's an important package. Then we have this broom package, which is also by RStudio, that help us to extract residuals and do residuals diagnostics. So that's what this package is for. means is a package that's going to help us to extract model means. So we're going to run a model, check the assumptions, they are all going to hold, and then we're going to extract means. means does that for us very easily. And multicomp is a package that's going to help us to do pairwise comparisons. I'm sure you've run into this. In my master's, I was taking a stats course that was teaching a lot of these concepts in SAS. And at least that time, maybe SAS has changed now, but at least in that time, when you do pairwise comparison, it was pretty much at least the way I learned, it was very like manual process where you would rank your means, look at the pairwise comparison p-values, start assigning letters and editing as you go. It was not reproducible for sure, and not very enjoyable process. So multicomp basically does that for you. So it's gonna look at those p-values of the pairwise comparisons, give you the letters already, easy, reproducible, very good package. All right, so if you are able to load all those libraries, those packages, the immediate next step here is for us to read the data set into R. So I left you the object name. Let's just add a assignment symbol, use the function read_CSV. You could use the read.csv as well, which is not going to matter here. And then open and close quotation marks. I'm sure you're getting tired of listening to me saying this, but we need to get outside of the other code folder. So // hit tab, select the data folder. So we go inside of it. And I have a few more things that you don't, but you want to click on that wheat_nk_bulk.csv, which is the data set that you just brought from GitHub. So if you run that, it gives you some messages here, nothing to worry about. And you should see now this object CRD_df on your environment. I'm just going to print this below and quickly talk about this. So this was a study that was conducted in Afghanistan, and it was an open source data that I found online that I thought was a really good representation to use here. Sometimes I make up data to be able to show you a concept. So if it is a made up data, I will tell you so this data. It's based on actual models, but is not observed data. In this case, it is observed data. That was a study conducted in Afghanistan, and this is basically a study that the reason why I selected this open source data to show here is because it was really it had a design very similar to what we were talking about in class. And so I wanted to give you an example of a data set that connects with the concept we talked about in lecture, and now we're using something that connects right here. So this study here had 9 treatments where they had 3 nitrogen rates, 3 potassium rates, and they measured a lot of things, but I am only giving you yield. So yield in kilograms per hectare. They have a rep column. Here you're gonna notice that, well, they have a rep column that has 4 reps, and they also have a treatment number for all those different treatments. One thing I want to maybe just highlight here and not getting into a lot of detail is that how R is interpreting these variables, right? So what is the class of these variables? So treatment is double, rep is double, N rate is double, potassium rate is double, and yield is double. So everything is considered numerical because we only have numbers under them, right? That's how R is interpreting them. And I'm pointing this out because it's going to become important when we wrangle this data and getting this ready for modeling. So just wanted to point that out at this point. So we have these 5 columns, we have 36 observations, which is the same number of observations that we talked about in the lecture, right? So our ANOVA tables should all match here. So what we talked in the lecture is going to transfer easily here. After doing the setup, so the setup is package loading, data importing, then we do some exploratory data analysis, and I'm doing just some tables and summaries here. I left you the code because we already saw this, so should not be new to you. We're just using the summary function to make sure that our numbers make sense, right? So I'm seeing here the rep is ranging from 1 to 4, so that makes sense. I have 4 reps. Nitrogen rate from 0 to 200 also makes sense. Potassium rate 0 to 60 also makes sense. And especially our response variable yield, right? So we're seeing here that yield is varying from about, 2,700 to 7,400 kilograms per hectare. This makes sense, biologically sensible. If I had a value here that was, 74,450 as my maximum, that makes no sense. This is where you would catch that and it would give you a chance of going back to it, check if it was, maybe a data entry error or something like that. Because if you do have something very abnormal in your data, it will for sure show up in your residuals. So if you catch it earlier, at least as far as outliers, and as far as that relates to outliers, you can find out what happened, right? So if you have a very high biologically impossible number of yield, it's probably a data entry error or something like that, that you can fix already at this stage. Next, so I mean, for us here, everything looks good. We don't have to do any of that. Next, if we come to use the glimpse function, is just a different way of showing our columns, showing the variable or the object class of those columns. So everything is double, everything is numerical. And this is an issue. We're going to talk more about it when we get to the wrangling side of things. So it is an issue that rep is double and nitrogen rate and potassium rate are double as well. All right, so we brought in data. We did some quick tables just to see if things were looking right or not. We found a few things that need to be changed. So I'm telling you, rep and rate and potassium rate are being seen as double. I do not want that. I want them to be seen as factor. Yes. For which one? For rep?
For
Everything is showing integer.
Not the doubles.
Okay, everyone is seeing integers? No?
Double.
Huh.
Maybe she used read that.
Yeah.
Because I bet never.
Okay. Yeah, okay, so let's talk through that. So Lisa used read.csv because she was getting an error from read_CSV, and that made a difference here. So she's seeing everything instead of double, she's seeing as integer.
I use .csv, but
You mean you use read.csv,
.csv,
but you're seeing double, okay. All right, well, I had a hypothesis, I don't have one anymore. I mean, it may be a computer difference, right? I don't think that's gonna matter though, because my guess is that it's considering these as integers because none of these numbers have like a decimal point. But it's still numerical, right? It's still within the numerical type of number. It could be an issue if, let's say, if your yield was seeing that as character. that would be an issue that person would have to do an extra step that others wouldn't. But I don't think that's the case. Being integer and double, I think it should be okay. And if, you know, I developed the script having on my side, things being double. If at some point you have an error that I don't, then maybe we can think about that. Maybe that's the cause of it, but I don't anticipate anything happening. Okay, so wrangling, right? We did a whole exercise on wrangling where we talked about a lot of different functions. Today, we're going to do a very light wrangling, and really every project that I do, every data that I analyze always has some wrangling associated with it. Sometimes it's very light, like here. Sometimes the whole project may be wrangling data. So in our case, what I do want to change here is first, the issue that I found was that, you know, rep and rate and potassium rate are being interpreted as double, and I want to change that behavior. I want to force them to be seen as categorical, which in R, you can also refer to that as factor. So I want them to be a factor. Pramod, did you raise your hand? Oh, okay. So I want to change that. The reason here, let me be very clear, because this is a subtle difference that makes a difference. So why should block be categorical instead of numerical? The reason is that, so we name normal, or the way that we refer to blocks is 1, 2, 3, 4 normally. But if you think about it, it does not mean that block 2 is twice as much as block 1, right? It has no numerical meaning. I could call them A, B, C, D, and that would mean the same, right? However, there is an issue that if we run a model where we include rep as, so in our model today, rep is not going to be part of the model. But when we do randomized complete block design, it will. And if we include rep as numerical or double in the model, instead of the model calculating an average for each block, is actually going to try to do a regression. So imagine it has block on the y-axis, and it has yield on the y-axis. Instead of doing averages for each one of the blocks, it's going to try to run a regression through those points, which is not what we want. So that's why we need to change rep. I guess today, for this exercise, we're not going to really use rep in the model, but I just want to create a habit of always checking this. Because, so let's say if you forget about this, and, you know, normally we give blocks numerical meaning 1, 2, 3, 4, even though it would be the same meaning as A, B, C, D. That's what we do as humans, I guess. We do 1, 2, 3, 4. You bring that into R sees just numbers and interprets that by default as numerical. Always. That's always going to happen. But that's not what you mean actually when you do run analysis with that. So you always need to keep an eye on this, and you would see this effect especially when you have your ANOVA table, when you print your ANOVA table, and if rep is part of your model, which again, for CRD is not part of the model, but for RCBD, it will be. So on RCBD, randomized complete block design, rep is going to be a line in your ANOVA table, and then you're going to be able to see the degrees of freedom. If it is a factor, it's going to have, in our case, 3 degrees of freedom, because it's 4 minus 1. If it is seen as numerical, it's going to have 1 degree of freedom, because now it's just using that to estimate the intercept of that regression over block, which is not what we want. And if you run an ANOVA table that has rep as one of its factors and it has 1 degree of freedom, you probably forgot to treat your rep as factor on the wrangling step. So I have to go back and do it. And as you know, why is that important? How does that matter? Well, it's going to change how your model is parameterized. And one of the things that's going to do as well is, if now you're only spending 1 degree of freedom on block where you should be spending 3, it means that you are artificially inflating the degrees of freedom of your error, which should not happen. I mean, it should not happen because of this, right? You can increase that by more reps, as we talked before, but not because you're running the wrong model or maybe having your variables being interpreted wrongly. And the same thing happens for nitrogen rate and potassium rates. So normally our study, in this case, we're going to have an exercise down the line where we're going to see what happens when you treat your treatment factors as numerical or as categorical. That difference is dictate what type of analysis you do. If I treat nitrogen rate and potassium rate as numerical, like here, the model is basically gonna run a regression for me. So instead of giving me treatment means, it's gonna give me an intercept and a slope across all those treatments, which maybe is what you need. Maybe that is what you want, but it's not what I want to do today. Today, we're doing analysis of variance, which for the most part means that your treatments are factors. They are categorical variables. So we need to make sure that we force R to see them as categorical instead of numerical. So that's what we're doing next year. So let's come here, add a pipe. We're going to use a function mutate. The first thing that I want to do is transform rep into factor. So we type rep equal sign. There's a function called factor. And you just say rep inside of it. So it's basically taking the column rep, transforming that into a factor and overriding on the current rep column. So if you just run this, and also assigning that to a new object that I'm calling CRD underscore DFW. I add the W at the end to make sure I know this is the wrangle version of the data. So if you print this now, you should see that under rep, now it says FCTR, that's for factor, right? So now we forced it to be a factor instead of being interpreted as a number. Even though the number is still there, but now it is a factor. I want to do the same thing here for N rate and potassium rate. There are a couple of different ways we can do this. You could come back inside of the same mutate, add a comma, and just do the same there. So N rate equals factor N rate. Get outside of that comma or the outside of that parentheses, add another comma. Do the same for potassium rate. So this is what I'm doing on my side. And once you print it now, factor N rate and potassium rate should be interpreted as factor variables or categorical. You can also think about it that way. The next step I want to do here is something that is actually only going to help us when we get to the end of the script, where it is when we do the plotting, so the publication ready plot. But I already want to do that here, just so we don't have to come all the way back up and rerun everything again. So add a pipe here, hit return, and use the mutate function. What I want to do here is create a column. So if you look at the data, we do have treatment, rep, N rate, potassium rate, and yield. I don't have one column where I have the treatment name. So let's say if I wanted to have treatment name, and think about it, maybe I want to say the treatment name would be 0 plus 0, where I'm on the same value, I'm saying this treatment here receives 0 nitrogen, 0 potassium. So I have a column saying that. That's what I want to do next here. So if you come on this mutate, I want to call this TRT name for treatment name. And again, there's probably a few different ways of doing this. The one I want to show you is using a function called paste 0. So the number 0, paste, and then number 0. You open and close quotation marks. So we are going to say here, what is the column that comes first? So that would be the N rate KGHA. I want to add a comma. And I want to say 0 plus 0, right? So to add a character inside of this function, you open and close quotation marks and add a plus right there. Then add another comma and then specify the potassium rate column. So it's basically taking the value from the nitrogen rate column and then pasting that into this string that now has nitrogen rate plus sign potassium rate. So if you run this and you print it, now you should have a column here that has that information, where the first number is the nitrogen rate, the second one is potassium rate. This is going to help us to plot this when it gets to the end of this script. All right, let's go to the next one here. So I want to ask for a summary of the wrangled version as well, just so we, I guess in this case, really the only difference is that now rep and rate and potassium rate are not showing a statistical summary anymore. When we ask for the summary of the unwrangled data, every time R sees a numerical variable, it gives you a statistical summary. When you ask for a summary, in this case, we're not seeing that because we transformed that to factor. And we also seen the treatment name column appearing there. So we do have 4 replicates. So you see here that these are so the first number here is the level of that. And then the second number is how many rows you have in each one of those levels. So we have 9 observations for each one of the 4 reps, and that's because we have 9 treatments. So things work out. So we have 4 blocks, 3 nitrogen rates in a factorial with 3 potassium rates, giving us 9 treatments, which gives us 36 36 observations, which again match the same number of experimental units, meaning that we have just 1 measurement per plot, which is what we should have here for running an ANOVA that does not have subsampling. And then just the range of yield there that we already talked about. Okay, maybe let's work on this chunk here, and that's probably the last thing we'll do for today. So, okay, we loaded the packages, read the data, did some EDA, just looking at the summaries, found some issues, fixed those issues with the live wrangling. Now now that the data is in the right shape as what is going to go into a model, I want to do another round of EDA, looking at some plots, so I can create some idea of what is the data telling me even before I get into a model, right? So the first one that I want to do here is just do a box plot on the nitrogen rates. So for that, please go ahead and start the ggplot like we normally do. The first thing here is going to be the data set name. So that is the CRD_DFW. We open the AES function right there. So let me print this data set right below and ask you all this so we can build this together. If I want to know what is the yield distribution for different nitrogen rates using a box plot, what would you specify on AES? Say that again. Okay, so X equals to N rate. I agree. Add a comma. I'm already gonna leave the Y there. So can someone else help me with what would go on the Y axis? Yield, right? So yield kg hectare would go on the Y axis. And then I do want to color my box plots depending on the treatment. So I just want to add that here already. So I'm just adding a comma there, and I want to say color equals to, in this case, I just want to color by nitrogen. So it's going to be nitrogen rate kilograms per hectare. If you come to the end of that, of all those parentheses there, add a plus. I mean, if we just run this, as you probably know, R is just going to create for you the canvas, but you have not asked for anything yet. Let's go ahead and add a plus and ask for a geom_box plot. If we run that, this is what we get. So it's giving us a box plot of the distribution of the data for nitrogen rates of 0, 100, and 200, which are our levels. Also giving us a legend on the side. We're going to take care of that. So the box plot is nice to see the distribution, but I also wanted to see all the data points here, right? So what we could do is we could add a plus, hit return, and add a geom_point. If we do that, it looks like this, which for this case, it may be fine. Sometimes, especially if you're working with observational data, machine learning type of data, you may have so many data points that it doesn't really make sense to show them in a straight line. So I just want to show you a quick trick. There are a few different ones, but one of them is instead of using geom point, we can use geom jitter, which adds some jitter to the points that they look a little bit like that. So now they're kind of like you know, it's keeping their y-axis is just jittering on the x-axis side. So it's not changing the true value of it, it's just giving some horizontal spread to your data. Okay. Also, something that I don't think we talked about as much, and I want to illustrate the concept. You know, so we have a legend here for the nitrogen rates, but we really don't need that legend because I also have separate, the nitrogen rates are also on the x-axis. So in this case here, this legend is not needed. If I wanted to remove the legend, there are a couple ways to do that, but the one that I want to show you is let's add a plus, hit return, and let's work with the theme function. So in previous exercises, we worked with theme underscore something, right? So underscore BW, underscore dark, underscore gray. There are many different predefined themes we can use. That's fine if you want to change your theme like that. However, if you want to change anything specific about any of those themes, you have to use this function that is only called theme. And then inside of it, you have a magnitude of different things you can change. The one that I want to change here is I just want to say legend. So there is an argument for legend dot position. I just want to say none. So that is going to remove that legend from the plot. Okay, so we don't have a lot of time here. So for now, let's just make sure you save your script. And also, let's do a stage, commit, and push. So everything we did today up until this point is going to be reflected as a commit in your commit history, both in your computer, but also on GitHub. So let's do that now. In next class, we'll continue on this script and we'll talk more about what this data is showing us. So if you saved your script by clicking on that floppy disks symbol, you come here on your Git tab, you're gonna click on to stage your script, click on that commit check button. We're just gonna, I mean, you can say something like CRD EDA, perhaps. As your commit message, you can commit it, close it, and push. And now all of your changes that from the beginning of the script until what we did to this point are reflected on your Git locally, but also on your GitHub. Okay, also before you head out, let me get your attendance on GitHub. All right, I just opened that issue. Make sure you claim your attendance. And then that's what I had for today. Next Tuesday, we're gonna most likely finish this exercise on the CRD. Yeah, and we're probably gonna have an assignment on it as well. So the assignment is gonna be like a take-home assignment that I'll be asking you to basically replicate everything we're gonna do on this script, but with a complete or with a different data set. I'm gonna provide a different data set and ask you to do that. All right, if you don't have any questions, you're good to go. If you do have questions, I'll probably stay for a couple minutes.
Yeah.
And if not, I'll see you next week.